Hey everybody, this is Larry. This is me going Q4 of the bi-weekly contest 161, number of integers with pop count depth equals to K1. Hit the like button, subscribe button, drop me in Discord. Let me know what you think about this one. Honestly, this one I took about 40 minutes, 35 minutes. I actually thought this was pretty straightforward in terms of ideas and understanding, but the implementation is tricky. So definitely, if you struggle with the algorithms part, still see if you can work on the implementation part. And it may take a while, and maybe it's fine, because I took a while. But the idea here is just that the constraints, right? K is equal to 5, that's okay. You could say that beyond 5, it doesn't really matter. Maybe they could have made K bigger just for fun, but it doesn't matter. And the reason is because 10 to the 5th, well, 10 to the 15 has only 50 bits, right? So it's 2 to the 50. So that means that after one iteration of this algorithm, it goes to a number from 1 to 50, right? And then I don't know, 6 maybe. They only, like, 50 only has 6 bits or something. I don't know, right? 6, 7. No, wait. Yeah, right, or whatever it is, or 8, whatever it is. It goes from 50 to 8, and then 8 to, I don't know, 3 or whatever, or 4. And my point is that after 5 iteration, everything is 0 probably, or 6 iteration anyway, whatever it is, right? And then the first thing, of course, to note is that with K is equal to 0, there's only there are no numbers that does that, right? Or wait, what did I put? I forgot. If there's only one number, which is the number 1, right? Because it is already, 0. I think they don't define it. Well, it's not here anyway. But yeah. So if K is equal to 0, we turn 1. I mean, I kind of already sneak peeked it here. So yeah. Otherwise, then now. So then now, let's go review what we just said, right? After one iteration from the number between n to 10 to the 15, it goes to a number from 1 to 50. So immediately I was like, okay, well, that means that we just have to count the number of numbers with that many bits after one iteration, right? And there are a couple of things that I did first, right? One is that I brute force. This is my brute force in that for I almost spoke code for some reason, just out of habit. For I from 1 to, in this case I will 60 just because it's a little bit bigger, but 50 should be enough, or 50 something if you want to be safe. I will 60 to be safe. Calculate the pop count, right? Or what do they call it? The pop count depth. Yeah, calculate the pop count depth, right? And that's it. That's what it sounds like, right? So for I is from 1 to 60. We save it down to we save it down. This is just a for loop, right? There are only 50 things. This only does like 3 or 4 loops, as we talked about, so not really worried about it, right? And that's it. We save it down, right? Oh, and you could actually, in theory, you could also do this recursively with dynamic programming, but like we said, there's only like 4 or 5 steps. Not gonna care about it, right? And this is just comedy. I don't know. I guess I cache it so that it doesn't go bigger. But yeah, the rest of this is a little bit more confusing. Honestly, like the idea is not that bad, but it's just about recursion, right? The way that I did. I mean, there are probably a lot of ways to write it, and maybe even cleaner ways than the way that I wrote it. But I'm here to explain my solution, right, and how I thought about it. And if you watch the live portion, I think I was slow enough to be giving my headspace, so definitely watch that if you want to go like step by step a little bit more. It may be a little bit slower because I didn't know the answers going in, right? So, but otherwise, yeah, my idea is that, okay, so let's say you have, and this is a binary number, you have something like this, right? And the idea here is just for me to split it into 2 parts, right? Because this number means you have the number of counts that are here, and then so basically you're splitting it from 1 to this, and then I think I did it not inclusively actually. So this is actually exclusive. I always forget which one's open or closed, but exclusive. right, whatever, right exclusive. Just put it that way. And then now from 10,000 to actual this number, right? So I break it down to two ranges. This one is actually inclusive, so maybe that's a little bit confusing, but you know, it's just about two disjoint sets, right? And here, the reason why I kind of break it down this way is that from here on the left side, on the smaller side, this is just right exclusive, means that if you have this number, and let me write it down here so that's more clear, is -1 is equal to this number, right? And this number is just, I don't know how many I drew, but this is just 8 bits, I want to say. If I miscounted, it's okay. It doesn't change the answer, right? So it's just 8 bits, 8 ones, and it is every possibility, right? I'm not going to draw over all of them because it's just too many. But you have 0, you have 1, you have then 1, 1 0 1 1 dot dot dot, but all the way to, you know, all the way to, you know, 1 1 1 1 1, something like that, right? But actually what you can do is also just draw out the prefix, right? So that here, right, right, something like that, right? Okay, you get the idea, kind of, hopefully, mostly. But the reason why we draw out the zeros is because then now you can look at it from each position. You can go left or right, a 0 or 1. And once you do that, then you realize that this is just the Pascal triangle. Or depending on how you think about it, you have Pascal's triangle or binomial thingy, right? Binomial, it's not the distribution. Maybe it is the distribution, but in any case. And what that means is that for 8 bits, you could kind of calculate it from Pascal's triangle, right? So 1, and the Pascal's triangle is this one where it goes 1, and then 1 1, oops, 1 1, something like that. And then it goes 1 2 1, right? I'm not going to draw the arrows. And then 1 3 3 1. And then 1 4 6 4 1 or something like that. I'm too lazy to even make the spaces, right? But 1 5 10 10 5 1 dot dot dot, right? So that's basically what this is all about. And what this is saying is that you know, for 8 bits, I don't know what it is actually, to be honest. It's not off my head. I'm not, but let's lie and say that it was never 8 bits and then say that it's only 5 bits, so then we have this number, right? And what this means is that now we have one case of 0 1s, right? 5 case of 1 1s, 10 case of 2 1s, 10 case of 3 1s, 5 case of 4 1s, and 1 case of 5 1s, right? And this is, you know, this comes from the Pascal's triangle, right? The number of 1s is just the number of right paths that you take, or left, depending on how you want. It's probably right. I don't know. If you do 0 and 1, then the number of right paths that we take in overall in the Pascal's triangle. That's one visualization. There are a lot of visualization. I'm just giving you the tie-in, right? So you can think of it in a lot of different ways, is my point. But around this point is that, yeah, right? But then that means that now you have 60, you know, and you could calculate this just by using Pascal's triangle. I honestly was too lazy to kind of, you could write the dynamic programming to Pascal's triangle, but I was just too lazy. In Python, there is a combination thing, so I just gotta use that because it only goes up to like 60 choose. The way that I did it, I guess it's not even 60 because 60 is just here, but it goes 50 choose 25 is the biggest number, but 50 choose 25 biggest number is still less than 2 to the 50, which is less than or maybe exactly the constraint, right? So that means that it cannot overflow, is my point, at least with the right rate of calculation, because definitely in other languages it might not, but the final result will not be overflow. The intermediate, maybe if you're using a language and you're not, you know, handful about it. But anyway, so that's basically what I have, right? So that means that given 5 choose 5 choose 0 is 1, 5 choose 1 is 5, 5 choose 2 is 10, 5 choose 3 is 10, 5 choose 4 is 5, 5 choose 5 is 1. That's it. That's what we have with this one. Okay, so that's how we broke down this thing with the 4 bits. And then now we have the other bit, right, of this. Well, how did I think about this? Well, the way that I thought about this is honestly just recursively. Almost like, what's it called? Digit DP, maybe some people made that way. But it's just 1. You could say this is this plus 0 to, and this is subtract. It's not subtract. Let me just rewrite this so that doesn't look like a subtraction, because it is a little bit confusing. This one was actually a subtraction, so that's actually why it's confusing. But yeah, right? So this means plus 0 to whatever this one is. Huh, did I have so many? I didn't alternate by accident. Huh. Okay, the alternation is not intentional, by the way. But yeah, and what this means is that, right, what does this mean? This means that there's 1 bit, 1, 1 plus whatever these things return, right? And then this is just now recursive, because then now, well, 0, yeah, I mean, 0 is just 0, so it is the original function. I guess this is technically 1. We just don't count zeros anyway. Maybe you have to handle 0. I actually did wonky. But yeah, now you have this number, right? And then now you go, okay, well, what is this number? Well, this number is just equal to 1 to, or maybe 0 to, depending on how you write it. 1 to whatever this prefix is. I don't know if I'm counting it right. And right, exclusive. And you know, to right. Like I said, maybe I have an extra 0 here. Do I? Oh, actually, no, that's right. Right, inclusive, right? And then you do the same thing. That's basically the whole idea, right? I'm not gonna go with the entire thing, but you get the idea of what I'm trying to construct to do, and that's how I kind of solve this problem. And honestly, the idea's not that bad, but I confuse myself with the notations. For example, for 1 here, I just kind of, I don't know, messed that up. The interpretation, but the recursion is pretty okay. So yeah, so that's kind of the idea, right? So let's go over the code. We have k is equal to 0, we return 1. Yeah, there's only one number where k is equal to 0, which is the number 1 itself. And since n is at least 1, it's always going to be 1. Otherwise, yeah. So cc sub I is equal to the number of ways that map to I after 1 step. That's what we talked about, and we have this f function, right? Yeah, and this f function, which order should we go? Yeah, let's just do the f function, right? So f function, we could go over, if x is equal to 0, then we just return, yeah, there's only one way to do the number 0, and everything else is 0 ways to do it. I just kind of return an array of 60 elements no matter what, so that I don't have to worry about off by ones or anything. Otherwise, we find the most significant bit, and what that means is that, like, for a number like we just have to find this bit, right? That's it. That's all this does. We find most significant bit, we break, and then we just, I is the position of that bit, so we just kind of count. That's the number. Technically, so yeah, 1 less than that. Well, that's the number of off shifts, so it's 1 less than that's the number of bits. So then we just do another function called cf, which calculates, given I bits, what is the distribution, right? And this is honestly, yeah, we just calculate it from this, yeah, from this function of the combination. So just I choose j, and again, that is binomial, right? Or Pascal's triangle, if you prefer, right? And that's, yeah, and that's it. So maybe you don't really need a function, though I prefer. Otherwise, then now we subtract this thing, and this is what we talked about, right? We just kind of subtracted, for example, in this case, you just kind of subtract out the prefix, right? Pretty straightforward. Yeah. Yeah. And then now you do the quote unquote the +1, the one that carries over, and this is basically this part, right? So because if the previous have one instance of 0, one instance of 1 or something like that, then you shift everything off by 1, right? Because now you have one more number for each of those instances. So this is the way that I kind of did it. I figured like yeah, we only call this once per bit because we always remove the most significant bit. So that means that this gets called at most 60 times. And I use 60, maybe it's 50, 60 times. So this only adds like another O of 60. So that's why I was like, it's fine. So it's going to be like n squared where n is 60 is my point. So again, not going to worry about the timing. Though you probably could do this in a smarter way. But basically it just shifts everything off by 1. Again, only 60 elements. And then now we're just trying, and the variable names are terrible because I was juggling too many things in my head, and I was doing this incorrectly for a long time already. So I didn't want to spare time thinking about variable names, so my apologies. These are live variables, and of course I would clean up afterwards if this is production code. But yeah, but otherwise, then now we just merge R and R2 by doing what's it called? I forget what I'm trying to say, but item by item addition, right? I forget what the linear algebra term is, what I was looking for, but yeah, yeah, and that's basically it, right? Because you just can't, because remember that this array is an element of 60, but it just gives you the distribution of how many, yeah, let me write it out actually. And this is true for all these arrays where R sub I is equal to the number of numbers that has I ones, right? As the bit count pop or whatever it's called, pop count, sorry. Yeah. And this is the same for R2, and then R3 just kind of merge them together, and that's it, right? Pretty straightforward for this one. And I don't think we already did that one. And that's it, right? So now this calculation gives us the number of numbers that maps to I after one step, right? Because now we count the numbers and we after one step. The only thing that a little bit wonky is that the number 1 technically maps to 1 after one step, but we want to, you know, because that's the only case where the depth count is different, right? That's where this is it. So then I just kind of move it to depth count 0 just to be more precise. You don't even need to move it to 0. You could just subtract this, I suppose, or even subtract 1 from the answer, maybe. Maybe. If k is equal to 1 or something, or k is equal to 1, yeah. If k is equal to 1, you have to subtract 1. I think that's the thing to do. But that's like a weird way of thinking about it. I think this is more natural, which is that, yeah, right, let me write. The number 1 has, well, actually, no, this is not more natural, but, yeah, I don't know. The number 1 has yeah, number 1 is weird. I just write that to be honest. And then now we just count over every bit, right? So that means that so keep in mind that fm of I is equal to how many steps it takes I to get to 1. So then yeah, if for example, if k is 5, or let's use a small example. If k is equal to 2, then that means that because the first step is to get it to here, right? So so if k is equal to 2, then you have one more step, and this is what yeah. If this is true, then we count the numbers that took one step away, right? That's where the -1 comes from, is the numbers that are one step away, and the numbers that are kind of k minus 1 steps away to make it k steps together. And that's it. And then we just sum up the count and we are pretty Gucci. Yeah, that's pretty much it. I just want to double check if I missed anything. Here's the top. We pre-calculate. This is brute force pre-calculation, is pretty straightforward. We just kind of wrap the combination. You probably could do a little bit of optimization here, but again, the numbers are only going up to 50, right? So it's 50 times 50, so it's 2,500 numbers. I'm not going to, or if you want to go 60 times 60, that's also maybe fine. But, you know, that's like 3,600 numbers, so not really worth optimizing for, even if it's a little bit sloppy, at least for me, because we only do it once anyway. But yeah, and here is the binomial, and here is the thing where we find the most significant bit and number of ones. Base case was a little bit awkward for me, for sure, because I was just kind of rushing it a little bit. But yeah, and this is just the bottom, and that's it. That's all I have for this one. What's the complexity, right? Well, this one is just a loop, so this is all of max, which is 60, pretty fast. So it's only calling this. Keep in mind that this, even if it's all ones, there's only at most 60 ones. So it does 60 recursion, and at each recursion, we do maybe this, you could say it's O of n, and this is O of max, and this is O of max. So at worst, this is going to be O of max square, which is 60 square, which is not worth thinking about. And that's it. That's all I have for this one. The submission doesn't come up because they're doing virtual contest. But yeah, I'm curious about my submission time, actually. Let's check real quick. But that is all I have for this one, though. Let me know what you think. Thanks for watching. And yeah, when this loads up, we can talk about it a little bit. I think it's fast, but I'm not sure. Yeah, 40 milliseconds. I'm not going to worry about it. But yeah, that is all I have for this one. Let me know what you think. Thanks for watching. And yeah, you could watch me solve a live then contest next. But I should have left a note for myself, because I was like, oh, remember to think about -1 later. But then I saw that everything's good. I just forgot. Silly mistake. Okay, anyway, Q4, let's go. Given two numbers nk, for any positive integer, define the following sequence. P sub 0 is equal to x. P I plus 1 is pop. Okay, the number one. Eventually reach the number 1. I guess so, maybe. Is if you get a power of 2. Is a P-count-depth of x is defined as the smallest integer d, such that P of d is equal to 1. For example, P to this and this is okay. It has the number of integers where the pop is exactly equal to k. Return the number of such. Okay, I mean, I have no idea. but it gets into a cycle pretty quickly, and k is equal to 5, which is interesting. I imagine it gets to a cycle, or not even a. Wait, what is the question? Popcount. Okay, because it just depends on the first number, right? The first number has at most, what is it, 40 or maybe 50? 50 bits. So it's just a number from 1 to 50, and then just counting the number of things that are with that count, right? That should be pretty straightforward in theory. Okay, so then now we just have to do it for 1 to 50, right? So, okay, let's just try it real quick. So let's just even go to 60, why not? Right, and then this is, I guess 0 is not a real thing, so we have to go from 1. F of I is equal to calc I, and then you could do it recursively, but it's fine. It is 60 numbers. What am I doing? Okay, so then while x is greater than 1, x is equal to x dot bit count, I think. Please forget. Return count. And we can print f real quick. And we should be able to match some numbers to it. Oh, whoops. 1 is 0, okay. 2 is 1. 4 is 1. 3 is 2. 5 is 2. 6 is 2. Okay. So we have all this thing. And then now we're just about mapping. What is k again? Oh, exactly equal to k, right? Yeah, and then just get about, for each number, getting the number of bits. Okay. Then it's just taking about the bits one at a time kind of thing, right? So let's say we have to this isn't binary. I just have a small number. That means that I have all the possibilities, right? So then sorry, I have to do it very dumbly because I forget my binary stuff. Right, so then now you have 1, 2, 3 cases, and then technically with a 0, which I guess doesn't really count for this one anyway. But the reason why I have it is for symmetry. You have 1 zeros, you have 3 1s, you have 3 2s, because of you want to do prefix, and then it just becomes binomial, right? Is that right? 1 3s, and then technically one more for 1,000. So okay, so then we can calculate that, right? Okay, so then you have binomial things. Okay, and then what if you have, okay, so that's the obvious case of what if you have like is it just 1,000 plus 10? Because 1,000, then now again we have the 1 3 3 1 distribution, then and then maybe one more for 1,000. No, because then it's 10. It's the possibilities of 10 plus the extra 1, right? So then now this is where the 0 comes in. So it's 1 plus 1 of the bit count plus f of 10 or something like that in binary. So then it's just everything shifted by that. Okay, that sounds reasonable. And 10 is just 0 and 1 in our case, plus the recursion of 1 plus 1 digit. Is that right? How does this recursion work? Oh, it's the number of things that are, well, in this case it's just 0, so that's why it cancels out. Okay, so then maybe what about we take a case like 1111, right? Then it's just 1,000, so it's f of 1,000 or smaller than 1,000, so maybe 3 digits, 111 plus f of 1 plus f of 111, which is the, confusingly maybe, the suffix here, right? And okay, which is fine. F of 111 is equal to, maybe we could redefine this recursively, is equal to f of 100, or technically 11 plus 1 plus f of 11. It's still confusing because of this prefix, but let's just say we have 101. Let's just have this, for example. Then now this is going to be 101, f of 101 plus 1 plus, oh no, this is 111 plus f of 101, right, on the count here, and this is defined recursively. And because they only branch once per bit, it should be okay. We just have to be a little bit careful about it, that's all. Anyway, and then 101 is equal to f of 11 plus 1 plus 01, which is just 1. And f of 1 could be 0 and 1. So then now we're Gucci, right? Yeah, okay. Because this is just, it's 2 to the 2, so then it's going to be 1 3 3 1. Okay, I mean, I think we got it. How much time do we have? I have an hour, so we should be able to figure it out. It's just, it's not so bad, but it's also not, I feel like it's very easy to make a silly mistake for me. But let's do the binomial. I guess we don't need to do a binomial, we can just cache it. Because it's only up to 50 anyway. Was it n over c, or c over n? Yeah, that's fine. So then now we can, I kind of want this outline, that's why. So then now we have Popcount-Depth is exact. So then now we just count the number of bits after one iteration. So then we just do k minus 1 from that. Okay, fine. Yeah. I mean, you can potentially optimize, but I don't really care enough. Okay, so then now we take the most significant bit, right? Okay, so maybe just redefine a number x. Okay, find the MSB, most significant bit, right? So for I in range from technically max. Yeah, so I got distracted by a dot. Okay, so if this is significant, then we break. And also if this is x, if x is 0, then we just return something like that, say. Otherwise, okay, so this is the most significant bit. So then now we subtract that. To get the, so then now we're breaking into this part, or this into this and this, right? Okay, so then now we have yeah, we get and I will f, but maybe there should be a calculated f. So f of but -1, or maybe just the number of bits is probably enough actually. Yeah, so then now this is going to be 0, 1, 2, 3. So there's 3 bits here, so that's fine, right? So that means that this is going to be a result. And then we also want to calculate this with all the addedness of the prefix. So maybe we have a prefix count or something. So then now we calculate the prefix of the new x without the most significant bit, and then pre plus 1. This is going to be this plus p for the existing number of things. And then we have R2 is equal to this maybe, and then now we just combine them. So for, I don't know, whatever. I'm writing really bad code, but it's fine. Bit pairwise thing, right? I need to figure out how to name these things better. I'm very not happy about this, but I don't want to spend brain cells on it quite yet, and because I feel like my brain track is stretched to the limit. This is technically p, I think, of the prefix that we had, and here we have maybe p times max. I don't know if this is quite right, but we can take a look. And then, is this quite true? Well, it is for every possibility, but it's not times max. Okay, fine. Because it has to be, yeah, because this is the number of bits, right? So that means that for using it as I is kind of maybe silly, but j is equal to what I call it, I choose j plus p, I want to say, maybe. And then now we have, yeah, f of n, right? Let me just print it before we do anything too funky. Okay, there's a lot of numbers, and this is clearly wrong because there should not be 1 on everything. Where did I do that again? Oh, this thing. Should be 0. Maybe 0 is fine. I don't know. Okay, so 4 you have 1 and 2, which is definitely not right, and 3 and 2 because it should be equal to the n, right? So this is definitely not right, but I suspect it is how I handle the prefix this case. But 4 is 100. So yeah, okay, let's see. X, P, R3. Okay, so X, so 400, so it does the 1 but it does 1 plus the suffix, and then oh yeah, that's why it's missing this part. How do I get this right? Maybe? I don't know, that's P maybe? Yeah, this is overcounting then now, right? Because this is 8 and not 7. I don't know if that's quite right either though, so yeah. So this isn't going to be right the way that, but it's something like this, right? Because this part, is this part right? For 3 is going to be, maybe this one is not right actually. Okay, so for 3 we have 2 1s and 1 2, and that's not right. So for the number 3 we have 2 bits. For number 2 we have 2 bits, so we have 2 choose 0. That's one way of doing it, which is true, but we should not count zeros. Okay, I just think I mixed that up. Okay, and then now we can throw away the all of 0 in general, maybe, because that never made sense anyway. So then now this is 4, okay, and this is 6, still not okay. This never felt right. I don't know how. Okay, that's at least we're getting closer without hacking, right? It's just 3, so then it's 4, which is 1 carrying this to 0 because that's no more bits. So that's definitely this case. And when it's this case, it is the prefix. And it's just one case. I want to write all when it's equal to P, but it clearly is not right. Okay, let's see how it is wrong here then. Okay, so 7, maybe that is a good case. I think the easy way to get 7, because 7 is a 1 minus whatever, but actually is a good debugging case though, because it should not have been. So 1 1 1 is just equal to F or CF of, we have 3 or 2 bits plus kind of 1 plus F of 1 1, right? And then F, this is equal to, let me just write this like this. F of 1 bit plus 1 plus F of 1, and then F of 1 is equal to CF of 0 plus 1 plus F of 0, right? Okay. Well, CF of 2 is going to be, we have 2 bits, so it's going to be 2 1s, or 1 2 1, say, right? 0 bits is just going to be 0. I mean, there's nothing here. Do I save that? Or is that right? Let's see, 0 choose 0 plus P. That's a little bit awkward actually. I don't know if this P is up. But it only updates 0, so maybe that's fine. I don't know. We have 1 bit is just 1, right? So 0 1. Technically 1 1, I suppose. Maybe I should print this CF. One, two, one, two, one, 1, 2, 2 is weird. Though it's maybe because of this P thing. So actually, maybe that's right. That's fine. Okay, let's pretend that's fine because it's 1 plus this. So maybe that's fine because it assumes that there's a prefix of 1. So this is 2, 2. Okay, and then 1 plus F1, right? And then now F1. This is just 1, but that's on the 0 thing, so it doesn't matter. F of 0. That's the major thing, right? What is F of 0? F of 0, I see. We should not return anything. Where is it? The code. We should not return anything and let the recursion do it, maybe. Yeah, okay. This P doesn't make sense, so maybe we don't do it. And then we just let the recursion. I don't know why I did it top down on this way. Okay, fine. Right. Okay. And then it's 1 plus this thing, kind of, right? So then now it's R2 of this plus 1. And then we can see. Okay, 3, 2 is too much, 6, 4 is too much, and also you have all these ones. I guess I have to choose where the 1 comes from. Where does it's 1 plus the recursion of things that exist. Is that true? Okay, so I mean, this conception makes sense. It's just 1 for everything that exists, but not all the zeros, right? So F11, it doesn't make sense. Yeah, F11. Maybe something like, yeah, if B is greater than 0, or do we 1 or something like that. Okay, so then now you have 3 and 5, which is still not right. I feel like the idea is right, but I'm mixing something up. If B is 0, if B is greater than 0, right? So that's 100. No, because in this case the 4 goes 0 all the way down. 4. It's not +1 on the count. That's why. It's not +1 on the count. It's the shift. I think that's where I confused myself. It's going to be B shifted by 1. Because it's 1. Yes, okay. I actually was thinking of that but then I just got confused along the way because it's very easy to. Okay, so then now we want to shift, right? So that means that, let's just say we multiply by 2 in a way. We shift because every count we add 1 to it. Yes. Okay. So that means that we want something like 2 is equal to this is kind of an ugly way of writing it, but it's fine even if it's n cubed. And then we move the last element just to keep it the same size. Okay, still no good, but is it closer? I don't know. Oh, that's where the 0 comes into play, because there should be, okay, yeah, because now is where you have this thing, because you have the zeros. The zeros actually matter again. Okay. Whoops. No, maybe too much. Why? If x is equal to 0, then just 1 plus this, right? So we have 1 0. We have 1 0, right? And then it just shifts it to a 2, right? Why is this wrong? I mean, I don't think conceptually is that hard, but I'm just being dumb. Okay, so if this is 0, R3 is really crazy. Do I manipulate? Oh no, this is 0 because, oh, that's a little bit confusing actually. Let's just write it. Why did I write it like that? Yeah, that looks okay. Okay, so 4. Okay, 0. Okay, so then now we can look at what R2 is. R2. Okay, this is what we actually expected, maybe. And then R. Why not? Why is it so weird? 1 2 1. Then why 1 4 1? Oh, I left this in here by accident. Whoops. I forgot to remove it. Okay, now we are almost cooking, but not quite. Oh no, yeah. This is 7. This is 4. Now we're cooking, right? So then now we have the distribution. I want to say. Also, let's try a big number. I'm using binary, but I'm not using binary. Let's just use a big number. Is that even right? I don't know. So if I don't know, maybe that's a little bit silly. But okay, we could do something easier. In that I know, yeah, because we did what's it? Calculator 2 to the. This is 2 to the 10. I know 2 to the 10. I don't need calculator. -1. So then this should be actually I don't know if this is the. It should be that binomial distribution if I'm right. But calculated in a way complicated way, or Pascal's triangle, if you will. Because it still kind of merge things together, and it seems like that's right. I googled it because I was too lazy to that should match exactly this function, but it calculated in a different way from the pieces components. So okay, so then now we're done, but we have to kind of convert. So this is after 1 pass. So to get k -1, so k can be 0. Okay, so if k is 0, then we're a little bit awkward. We have to do k is equal to 0. Okay, have to do k is equal to 0. Have to do k. I'm sorry, I'm repeating it because it's so easy for me to mess up. Okay, what's k equal to 0? K equal to 0 means that the pop count depth is exactly equal to 0. Which is only 1, right? Is that right? Is that only the number? Is that true? I don't know. And then for other cases, then it is just f of n of k -1, maybe something like that. So 1 3. Oh, 2 3. This is 1, this is 3. Why? Well, that's sad. Okay. I mean, okay. 4, what is a 4? 4 only has 1 bit, so 4 takes 1 step. That's right. 1 takes 1 step. 2, what? Oh no, 1 takes 0 step. Maybe I handled 0 incorrectly in this one, because I think I just assumed that 0 is whatever. But oh no, because of this thing, this I also assume 0. Because then you have 0 has 0 pop count. But does that matter? It does look a little bit weird for sure, because this is no, this is fine as long as you count that 0 is in it. But why am I wrong? 1 and 3, Okay, so 1 is pop count 0, 2 takes 1 step as we know, 3 goes to 2, so then 4 goes to 1 after 1 step, so this is also 1 step. So it's, and 0 is just weird, so maybe I handled that weird. I think the number 1, I don't handle the number 1 correctly, that's why. I don't handle the number 1 correctly. Okay. I don't handle the number 1 correctly, which is true. Which is true. Because I assume... Yeah, no. Because 0, I handle 0 as 0. But 1, what do I handle 1 as? So we're close still. But I don't handle 1 correctly. So 2... what do I print here? Hang on. I don't think I used the F, that's why. Well, okay, I have 2 things named F actually, so that's pretty bad. I think I have to map this. Oh, that's right, I'm being dumb. So this is after 1 step. This is after 1 step. How many counts after 1 step? I'm mixing things up. But we're good. I'm just mixing things up. And I keep calling everything F, which is not great. But, for F map, I don't know if that's quite right. Okay, so then now, this is the number of digits after 1 step, right? Yeah, let's go see. C sub I, what's C sub I? How much time do I have left? 39 minutes. Is equal to the number of numbers that maps to I after 1 step. But that doesn't mean the number of steps, right? So that means that then now it's for I in range sub max, if C sub I is equal to k minus 1, count we added by, no, this isn't right. This is if F sub I is equal to, then C sub I is, there needs 1 more layer, that's what I forgot. So then it maps to how many numbers of 1, right? So I is the number. No, maybe this is fine. Maybe this is right. Yeah, something like that. Okay. Yeah, I am confusing naming things a bit. Okay. C is now associated with enclosing. Oh, I keep on naming things. Naming things is so hard. Okay. F of I. Oh, it's FM of I. Naming things is hard. I forgot. Okay. Okay, 4, 3. Okay, not quite what I expected, but that's fine. Why? FM sub I, right? So I, FM sub I. Okay, 0. Okay, K is 1. Is it K plus K minus 1? Because it should not be. So K minus 1 means that it's 0 steps after this. So it should be the number of 1s, right? So that's right. Then why is it not right? Maybe it is, I don't know. Oh yeah, because it's 1 plus 3, right? I mean, there's no way to get 2 from this anyway, but I think the after 1 step is confusing, because after 1 step 1 becomes a 1, but it is not a 1. That's the critical part. But only 1 number is 1 before the step, right? So maybe we can write this and then CC of 1 divided by 1, CC of 0, maybe. Okay, still not right though. At least the way that I have it. Well, 0, 0 should not, no number should map to 0 after. Yeah, so maybe I don't even think I did the math from 1. I just kind of, you know. Okay, so this looks kind of right, but honestly, at this point, I feel like I'm hacking a lot and not like, you know, like I'm almost finagling with the data kind of thing. So I'm not super confident about it. But actually, let me double check. This one, I mean, kind of makes sense, but I can double check this one, which is maybe more important. So we have 3, because they all map to 2 after 1 iteration. So I guess it's consistent. Whether it's right, I don't know. All right, YOLO. It's gonna be wrong, but oh, I mean that took way too long. But and there's just so many things to forget. But I'm actually surprised I got it right on the first try. But you know, still a little bit on the slower side for sure. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.